Okay, let's start by graphing f of x is equal to sine of x. Keep in mind that we are no longer calling the inputs theta to emphasize the fact that they're angles. Now we're calling them x to stay consistent with general function notation. This could be a little confusing since sine corresponds to a y coordinate and cosine corresponds to an x coordinate after rotating by an angle, which we are now calling x. So that could be confusing, but try to see past that confusion and know that x is just the input angle of rotation. So let's start with sine of x and make a table here. So here are conveniently chosen x values from 0 to 2 pi in increments of pi over 2. Can you fill out the corresponding sine values? Of course, you can use the unit circle at x equals 0, or the angle of 0. Notice that the y coordinate is 0, so the sine is 0. And then at pi over 2, the y coordinate or the sine is 1. And then we can continue like that, right? So at pi, it would be 0. At 3 pi over 2, it's negative 1. And then at 2 pi, it is back to 0. And after 2 pi, it starts to repeat itself. So that's why we're only doing from 0 to 2 pi, because after that, it's just the same thing over and over again forever. So at 0, it's 0. At pi over 2, it's 1. And then 0, negative 1, and then 0. So we can see these points appear over here. So this is a part of the sine graph. And now the question is how do these points actually connect together? Now, it's worth considering on your own, is it just a straight line here from 0, 0 to this point over here, pi over 2, 1? Is it just a straight line? And if it's not a straight line, how is it different than a straight line? So take a second to think about that. Luckily for us, we know the unit circle like the back of our hand, or at least we should. So in particular, we know pi over 6, pi over 4, and pi over 3, which are all in between 0 and pi over 2. So we can actually, if we have the table memorized, which again we should, we can plot those particular values. So after 0, we can plot pi over 6. That has a sine of 1/2. And then pi over 4 has a sine of root 2 over 2. And pi over 3 has a sine of square root of 3 over 2. And so again, we can see that, this from this x equals 0 to x equals pi over 2 in terms of angles corresponds to this piece of sine over here. We can see that it's above the line from 0, 0 to pi over 2, 1. So that implies that sine initially increases quickly and then starts to sort of plateau a little bit. And that should make sense, right? Because initially, when your angle is increasing from 0, all of this is just vertical change. So your sine is increasing, your y coordinate is increasing like quite a bit. But when you're all the way up here, when you're this close to pi over 2, for the same amount of angular change, it's much flatter of a movement. So your y coordinate or your sine is only increasing very little, which corresponds to this flatter component of the sine curve over here. So let's see how the sine curve actually looks if we plot the rest of it. And yes, it obviously goes through these points. And we can see from 0 to 2 pi, it makes sort of this wave shape, which repeats forever in both directions. And just to make sure that you can think through every piece of this curve, so from 0 to pi over 2, that corresponds to this piece of the sine curve. And then you can see that from pi over 2 to pi, it's just the same thing in reverse, which makes sense because the y coordinate when you go from pi over 2 to pi is just the same thing that happens from pi to pi over 2, but going backwards. And then from 0 to pi, that same journey is then like you take the negative of those values to go from pi to 2 pi. And that makes sense because as you rotate from pi to 2 pi, your y coordinate is the negative of what it would be if it was rotating from 0 to pi like this. Okay. Now, what about cosine? Let's see. So cosine, we can do something similar, right? We can just, well, first let's hide the sine. and then we can plot the same values for cosine. So can you plot these values for cosine? So for, again, now at x equals 0, that corresponds to an angle of 0. That cosine is now the x coordinate, so that's a cosine of 1. And then it's cosine of 0, negative 1, 0, 1. So 1, 0, negative 1, 0, 1. Nice. And if we plot the actual cosine curve, we can see that it actually looks suspiciously similar to the sine curve, doesn't it? If we plot them at the same time, we can see that they actually look like horizontal translations of each other. In fact, if we take the sine curve and we shift it pi over 2 to the left, it looks like we would get the cosine curve. So if we take the sine curve and shift it pi over 2 to the left, so that's what this transformation corresponds to, we get the cosine curve, or so it seems. And Wolfram alpha confirms indeed that that is true. So that's pretty interesting. It actually gives us a link between sine and cosine. So if you have a function in terms of sine, one way to turn it into cosine is to just remove pi over 2 from the argument of sine. And, similarly, if you have cosine and you want to convert it to sine, you can just add pi over 2 to the argument and convert it to sine. Now, another way of sort of seeing this is actually on the unit circle. So sine of x plus pi over 2 is equal to cosine of x. So think about this angle right here, and we could actually rotate this point around this center. So transform, rotate 90 degrees. And then we can construct a segment to visualize it. And notice this, so this corresponds to x, this point corresponds to x, and this point corresponds to x plus pi over 2. The x coordinate, or cosine of this angle, is the same as the y coordinate, or the sine of this angle, no matter where this point gets rotated. Does that make sense? So over here, notice that the cosine of this is 1, and the sine of this is 1. And as you move this, the cosine of this, whatever x coordinate corresponds to this point, is the y coordinate that corresponds to that point. And you should be visually convinced of that. So there's two ways of seeing this relationship. One is on the unit circle, and then 2 is on the graph. So we can keep transforming trig functions to gain understanding. So if we start again with sine of x, if we shift it to the left pi over 2, we talked about how we get cosine of x, but what if we shift it to the left an entire pi? Or shift it to the right an entire pi? Either way, this maximum would end up above a current minimum. And so if we go ahead and plot such a function, it looks like the two functions are negatives of each other, or in particular, sine of x plus pi looks like it's the negative of sine of x. And just to convince you that it would be the same if I did minus pi, take a look, it's exactly the same. And that shouldn't be surprising since x minus pi and x plus pi are 2 pi apart, and of course the period of sine is 2 pi, so adding 2 pi to the argument shouldn't change the function. But in either case, it looks like the functions are negatives of each other. So sine of x plus pi looks like it's negative of sine of x. And in fact, that is true. Not only is it true, it's also true for cosine. So if we look at f of x equals cosine of x, and g of x equals a shifted version of cosine, specifically by pi, again, we see that these two functions look to be negatives of each other. So cosine of x plus pi looks like it is the negative cosine of x. And in fact, that is also true. Now, we can clearly see that is true on the graphs, but we can also clearly see it on the unit circle. So if we think of this angle as x, this angle can be thought of as x plus pi or x minus pi. Either way, it's diametrically opposite to this point. And one other way of thinking about diametric opposition is you could think of this as being reflected over the y-axis and then over the x-axis to get this point. So in other words, the x and the y coordinate of this point are the negatives of what they are at this point, which is why the sines and the cosines of this angle are the negatives of what they are at this angle. So that should make sense, but we could consider, how does it work for tan? So tan of x plus pi, by definition, is sine of x plus pi over cosine of x plus pi. But we just talked about how that's negative sine of x over negative cosine of x, right, using the facts that we just developed. And then the negatives are going to cancel, and that's just sine of x over cosine of x. And, well, of course, that's just tan of x. So long story short, it looks like tan of x plus pi is simply equal to tan of x, not equal to the negative of tan of x. So this also tells us something that's more interesting, is that if we shift tan, the graph of it, to the left or to the right by pi, it actually lands on top of itself. And pi is actually the period of the tangent function. So before we graph tangent here, we can convince ourselves a little bit more that we understand tangent on the unit circle. So keep in mind, again, this is x and this is x plus pi. They have the same tangent, and that should be insanely clear based on this picture, because tangent is the slope of the radius that corresponds to the angle. And obviously, this radius over here and this radius over here are on the same exact line. So of course they have the same slope. So it's a really, really powerful way of seeing that the tangent of an angle is unchanged when you add or subtract pi from that angle. Now, to get an idea of how tan actually changes as we move it, well, first we can hide this segment here. So let's hide that. So starting at 0, so at an angle of 0, the tan here is the slope of this radius, which is 0. So 0 comma 0 is going to be on the graph of tangent. Now, as we go toward pi over 2, what is happening to the slope of this radius? Well, it's certainly increasing. And right over here at pi over 4, the slope is 1, so the tangent is 1. But as we get closer and closer to pi over 2, we start to notice that the slope gets incredibly large. So right now, I don't even know what it is. It's probably like 100. And now it's maybe like 1,000, maybe 10,000, maybe a million here, maybe a billion, maybe a trillion. And we're going to get to every positive number in the entire world before we get to the straight vertical point where it is going to be undefined. So it's basically going to approach infinity as you are getting closer and closer to pi over 2, but never quite get there because infinity is not a number. And going from 0 to negative pi over 2, we can see the slope is decreasing, it's decreasing, until again, when you get close to negative pi over 2, it starts to get close to negative infinity. And since the period of tan is pi, repeats every pi, that shape, whatever shape that carves out, is going to repeat over and over again. So clearly there's going to be some vertical asymptotes at pi over 2 and at negative pi over 2. And we can now see it for ourselves. All right, here it is. So as promised, 0, 0 is indeed on the graph. And as you increase toward pi over 2, tan grows without bound. Right? So we're getting really, really high values. And the same is true as you approach negative pi over 2. You get really, really negative numbers. And so the graph of tangent is a little trippy, but here it is. So let's practice starting with graphs of trig functions and finding an appropriate equation for them. Of course, there's an infinite number of answers, but let's try to find the simplest one, starting with this one. So this one starts at 0, 0, and then goes up to its maximum before returning to its midline, where the midline is the horizontal line around which the wave oscillates, and then it goes to the min before returning to its midline. This should remind you a lot of sine of x. So if we plot f of x equals sine of x separately, we can see that it does pretty much the same thing, right? It starts at 0, 0, and then it goes up from there, or it starts from its midline and goes up from there, more generally. And negative sine of x starts at the midline and goes down from there before repeating itself. And cosine of x starts at its maximum value, so this does not start at the midline, like sine and negative sine, and then it goes down from its maximum. And negative cosine starts at its minimum value, and then it goes up from there. Now, it's helpful to know that, because when it comes to modeling these curves, having these in your back pocket is very handy. because when you see a curve like this, you immediately recognize, oh, this looks pretty much like sine. The only thing that's different, though, is it's been vertically scaled by a factor of 3, it looks like, right? So because that's at pi over 2 comma 3 instead of 1, and that's negative 3 instead of negative 1. So the amplitude of this wave is 3, not 1. So the amplitude of a wave is the distance from the maximum or the minimum to the midline. So this looks like 3 times sine of x, which it is. All right, what about this one? Well, this starts at the maximum and goes down from there, so cosine seems appropriate. And the only thing different about it is the midline. The whole curve has been shifted up 1. So this is f of x is equal to cosine of x plus 1. And indeed, it is. All right, what about this one? Well, this looks like it starts at the midline and then it goes down. So this looks a lot like negative sine. And in fact, it is exactly negative sine of x, as we can see over here. Now, again, you might have said sine of x plus pi or sine of x minus pi, and that would be perfectly fine. In fact, you could even use cosine here. Maybe you started with cosine and moved it to the left pi over 2 to get this graph, which would also be completely fine. What about this? So this is also looks like cosine here. It starts at the max and goes down, but the period, it starts to repeat itself every pi instead of 2 pi. So it's been horizontally compressed by a factor of 2. So this is f of x is equal to cosine of 2x. And finally, we can think about this one, which is a combination of a few things. So it's tempting to start with negative cosine, but in order to make this problem more fun / hard, let me just ban that. Because it's a great idea and it makes the problem a little easier, but just for max difficulty, let's do this with sine. So can we start with f of x is equal to sine of x and transform it into the equation that we have here? Well, the first transformation that I like to make is the period adjustment, aka the horizontal compression / stretch. So what's happened here? Well, it looks like the period is now 4 pi long instead of 2 pi. So it looks like a horizontal compression by a half has occurred. So it really looks like we want sine of 1/2 x to make the periods the same. Okay. Now, how do we make the amplitudes the same? Well, the amplitude of sine as it is now is 1, but the graph that we're going for has a midline of y equals 3, it looks like, and it gets to 5 and 1, so that's like a distance of 2 away from the midline. So it looks like it's been vertically scaled by a factor of 2. So it looks like 2 times sine of 1/2 x. All right, and now, I just referred to the fact that the midline was 3, so it looks like the whole thing has been shifted up by 3, so let's add 3. And now we're very close. We just need to shift it into place. So we need to shift this point so it lines up with over here, which is halfway between 0 and 2 pi, so that would be pi. So we need to shift our graph to the right pi, and that corresponds to this. If you're not familiar with function transformations, you might want to do a review on that, but we need to replace x here with x minus pi, and that shifted to the right pi, and now we have exactly the function that we want. Now, this coefficient right here, 1/2, in general, that 2 pi divided by this number will give you the new period if you're talking about sine and cosine, which it does in this case, right? It gives you 4 pi over here. And if you're talking about tangent, you want to do pi divided by whatever this number is, because this is a compression factor horizontally, so it's going to affect your period. So keep that in mind if you have a question regarding the period. And also, if you want to graph an equation, so if you want to go backwards, it's pretty much the same process. So if you have this equation, you want to graph it, you can apply the horizontal compression by a factor of 1/2, and then the vertical stretch by a factor of 2, and then you can shift it up 3 and then to the right pi, and you will end up getting this graph. So starting with, of course, sine of x. All right, with that said, have fun doing your homework, and see you next class.